In this video, we are going to talk about the problem number 5 in the IMO 1971. The problem states that prove that for any natural number m greater or equal to 1, there exists a finite set S of m of points in the plane satisfying the following condition. If A is any point in S of m, then there are exactly m points in S of m whose distance to A equals 1. Let me illustrate what this problem is talking about with a picture. When m equals 2, you can simply take this S of m to be the set of 3 points which form the vertices of an equilateral triangle of set length equal to 1. So every vertex, every point in here, will have exactly 2 neighbors whose distance to it is equal to 1. So m equals 2 case is very easy. The difficulty of this problem is that when m gets bigger, it's really hard to draw a picture. So instead of just using geometry, we'll have to think a little harder to use tools from algebra or combinatorics. The idea of the proof is the following. Instead of constructing the points in S of m directly, we are going to construct the vectors that represent the distances between points in S of m. And we don't look at all the distances. We'll just look at those distances that are equal to 1. So with length equal to 1. And we'll do this by induction. And here are the details of the proof. We'll construct the sequence of vectors that represents distance equal to 1 as follows. We're going to write this as a claim. Claim. For any m greater or equal to 1, there exist vectors u1 through u sub m in R2 such that number 1, the length of ui is equal to 1. So they are unit vectors. And second, we look at the linear combinations. C1 U1 plus delta CM UM for all C1 through Cm taken from -1, 0, or 1 with at least 2 of C1 through Cm non-zero, so that this linear combination will not boil down to the case of a single vector u sub I or 0. We will require the length of the vector formed through this linear combination to be non-zero and also not equal to 1 for all such C1 through Cm's. That is the requirement. Namely, whenever this linear combination is non-trivial, then the length of it is also non-trivial. So this is a claim, and we will prove it by induction. If m is equal to 1, then the claim is trivial. We can just take u1 to be any unit vector with length 1. And now we assume the claim is true for m minus 1. Namely, we have found u1 through u sub m minus 1 satisfying those two properties. So this is our induction hypothesis. Okay, now how do we find u sub m? The rough answer to this is that this u sub m exists because of the so-called infinite pigeonhole principle. And you will soon see what I mean by this. First, there are infinite many choices of a unit vector in R2. And second, there are only finitely many choices for a vector in R2 that violates our property number 2 with x equal to u sub m. By this we mean there are only finite many x in R2 with this guy equal to 0 or 1. For some C1 through Cm in -1, 0, 1 with at least 2 of them non-zero. And if you combine the first and the second, you will see since there exists infinite many choices for the unit vector, but on the other hand, there are only finite many choices for x that violates number 2. So there must exist a choice of u sub m that makes both 1 and 2 hold. In fact, there should be infinite many choices for u sub m. But we have to justify the second one more carefully. We'll look at the following two cases. If C sub m here is 0, then whenever there are at least 2 of C1 through C sub m minus 1 non-zero, by induction hypothesis, we always have the length of this linear combination not equal to 0, 1. This is precisely our induction hypothesis. Right here. But now if C sub m is non-zero, then by our assumption, at least one of C1 through C sub n minus 1 is non-zero. And it follows that this linear combination must be non-zero. That is because if precisely one of them is non-zero, then this will boil down to a single vector u sub I, or negative u sub I, which is non-zero because that vector is a unit vector. If at least two of them are non-zero, then this guy, by our induction hypothesis, is not equal to 0 by the property number 2. So this is also by induction hypothesis, plus a trivial case. Now, in this case, we're going to look at the situation where the property number 2 is violated. When 2 is violated, then there exists a solution x to either this system of equations or this system of equations. However, if you count the number of solutions to this system or to this system, you'll realize that there will be only finite many choices for x in either case. For example, what are solutions to this system? The solutions to this system are the points on the unit circle that is equal to this guy, or the negation of this. So plus and minus cases will contribute to at most 2 points, or 2 solutions in this case. And what about this system? The solutions to this system must lie in the points where 2 circles, 2 unit circles, meet. So x must lie in here or here. Plus and minus cases will give us 2 times 2 equal to 4 cases at most. And of course, here we have used the fact that this guy is non-zero. Because if this is 0, then those 2 equations are identical. There will be infinite many points. That this guy is non-zero follows from our discussion here. Okay, anyway, we have showed that there are finite many choices for x in either case. That is just for one instance of C1 through Cn-1, with at least one of them being non-zero. And because each C sub I can be -1, 0, or 1, the total number of choices for C1 through C sub n-1, with at least one of them being non-zero, is 3 raised to the power n-1 minus 1. That one case is a case when all of them are equal to 0. So the number of x which plays a role of um that violates So property number 2, where number 1 holds, will be less than or equal to 2 plus 4 times this number. Anyway, this is a finite number. Therefore, there exists U sub m in R2 satisfying number 1 and number 2. And this finishes the induction and verifies the claim. And now we are ready to find this S sub m. We'll take S sub m to be those linear combinations. This is clearly a finite set. Now, for each point in S sub m, we're using vectors to represent points. For each point in S sub m, say this is equal to, there will be precisely m points whose distance to this point equal to 1. They are the following m points. Y1 is a point where you change C1 from 0 to 1 or 1 to 0. 1 minus C1 times U1 plus C2 times U2 Cm times Um. The last vector will be Y sub m equal to C1 times U1 plus Cm minus 1 times Um minus 1 plus 1 minus C sub m times U sub m. You flip the last coefficient from 0 to 1 or 1 to 0. Indeed, the distance from y sub I to y will be 1 minus 2ci times ui, the length of this. But ci is either 0 or 1, so this is equal to the length of ui, which is 1. And those y1 through ym are distinct m vectors. Why are they distinct? They are distinct because, say, if you look at the difference between y1 and y2, this guy, because C1 and C2 are either 0 or 1, so the length of this is either the length of U1 minus U2 or the length of U1 plus U2. They are all non-zero. Barrel construction, because at least 2 of the coefficients are non-zero, so this is non-zero barrel construction. Those y1 through ym are distinct. And furthermore, any other points in S sub m will have distance to this y not equal to 1. This is because of the property number 2. Those m vectors are precisely the cases where you change just one coefficient of this linear combination. But if you change at least two of them, then you will change the distance. That distance will not be equal to 1. So more specifically, if X is this linear combination with at least 2 C sub I prime not equal to C sub I, where the C sub I is the coefficient of U sub I in Y. Then if you look at the distance of the difference, this guy must not be equal to 1 by the property 2, since there are at least two coefficients non-zero. This shows this S of m we constructed here really satisfies the requirements of this problem. So S of m is as desired, and we are done.